Okay, so hello everyone. My name is John Mertens, and I'm a principal engineer at change.org, and I'm here to talk to you about our experience using Elixir, specifically GenStage and its lovely abstraction flow, and lessons learned from pumping a ton of data through it. I'm glad Miriam spoke first, because that gives you a nice background for what I'm going to get into. So, Change is primarily a Ruby and JavaScript shop, but we started using Elixir in early 2018 to build a high-volume, mission-critical data processing system. Now, I won't go into too much detail on our adoption story. That's not why we're here. But suffice it to say that during all the early-stage meetings about this new system, someone kept bringing up how Elixir had this amazing library flow, and it seemed like a perfect fit for our problem. Now, I get as granular as I'm allowed to when it comes to details about our system, but the general flow is like this. Something happens on change.org, a campaign update goes out, a petition is signed, a victory is declared, something. And in usual distributed system fashion, there's an event log, events get fired, there's a message bus, and in some cases, specific cases, an event gets added to a queue. Now, our system pulls these messages in, preps them, transforms them, applies some business logic, and then generates some side effects. And then depending on how everything goes, the message is either passed on to some other queue, it gets discarded, or maybe retried. And so far, everything's gone swimmingly. Sure, there have been a few hiccups, but there's no real showstoppers. And while I'd love to say that was solely due to my brilliant team, that would only be half true. Which brings me to the first lesson that we've learned with Flow. Flow is awesome, like seriously, and I will dig into a couple reasons why. First is parallelism. Parallelism is awesome, especially in a large-scale data processing system. And now, while parallel processing has always been possible in Elixir, Flow's abstractions make utilizing it a no-brainer. You can write code that looks essentially like regular old Elixir pipelines, and then when you run it, you can be sure that all your CPU resources are going to share the load. Here's a totally contrived example of what I mean. So you can see here, we're building an infinite stream of the numbers 1 through 5 and then squaring each one, just doing some arbitrary work. And if you run this in IEX and open up Observer, you can see there's only one scheduler working on it. It's the green one. The orange one's actually the Observer process, and I'm not good at Photoshop, so it's still there. But if you do run this locally, be sure to kill it, because there's no end, and we'll just use up all your memory. Now here's the same trivial code rewritten in Flow. Looks nice. If you run this in an IEX shell and pop open Observer, you can see that all the schedulers are working on it. The point of this is that you can write your data processing functions the same way you would write your normal Elixir pipelines. It's just that now the work is spread across all the CPU cores. So I feel like we're all on board with parallelism, so I'll move on to another brilliant feature of Flow. Backpressure out of the box. Okay, technically this is a feature of GenStage, but Flow is an abstraction over GenStage, so I'm going to count it. Basically, whenever I refer to Flow, it's Flow and GenStage. Now, backpressure is where your system asks for more data instead of data being pushed to it. Now, backpressure is one of those features that I didn't really understand how amazing it was until I was reminded of one of the main problems in systems without it. DDOSing yourself. Oh, it stings every time I think about it. If you come from a Ruby background like myself, you're probably familiar with using a system like Sidekick or Rescue to process data. And then one of those situations, suppose you get like an influx of events to process. Your queues start to back up, so you spin up some more workers to process the events, and then the dependent systems that you're using to process the data start to get overloaded by the increased worker count, and before you can get more workers spun up there, bam, you just gave yourself a denial of service. And to be honest, I'd actually forgotten from like the last year working in Elixir, forgotten about the old self-DOS until I recently saw this Slack message at work. It totally made me remember. And now the backfill mentioned in this process is running in a Sidekick-based system, and the person posting the message is doing the current best practice. Do a little math up front, monitor the situation, and then keep the DevOps team in the loop. That's where they posted it. It's got to be a better way, right? So with flow, your data processing is in charge of requesting more events, not the other way around. So this means that if your processing is dependent on some other service, and that service becomes slow, then the flow will slow down accordingly. Nobody gets overloaded with requests, and the whole system stays up. And following that train of thought, if the system starts to get more performant, flow just follows it right back up. Now in our system, for example, we regularly just increase the volume of data going through the system by adding new types of data to process. And each time we do it, we basically don't really ever worry about knocking over a dependent system. Worst case, our queue gets a little bit backed up. We spin up another worker. So now that we know some of the baseline advantages of using flow in GenStage, I want to touch on a couple of lessons that we've learned that fall under the broader topic of just take the time to organize your flow. What do I mean? Well, first of all, keep your flow simple. Flow and GenStage are very powerful libraries that enable you to do some pretty wild data pipelining gymnastics, but I'd recommend at least starting simple and only increasing the complexity as the constraints of your system require it. So essentially, the more straightforward you can make the flow, the easier it will be to reason about. And I like this line from the flow.partition section of the docs. Describes a concept called embarrassingly parallel problems. To me, this highlights an ideal state that we should strive to get all of these processes to. So if we can rearrange our problem into an embarrassingly parallel problem, then flow can just really shine. We're not there yet, but that's what we're getting to. Also, in the same flow docs, there's a section called performance discussions, and the first suggestion, it says know your code. Then it proceeds to describe a handful of problem-specific optimizations you can make to the canonical word counting example that's throughout the flow docs. But I think that know your code advice also extends to your whole system, and I'll mention that a few more times in this talk. In our particular case, we use SQS for queuing, and as you'll see, we take that into account when building our flow pipelines. So with all that context in your brain, let's take a look at some code. Psych. First, I want to give a quick background on SQS for those who haven't worked with it. I'm going to speak fast because it's not super important, and this isn't a pitch for SQS, but it's a thing that we use, and in the spirit of knowing your system, I'm going to just explain it real quick. So SQS, or Simple Queue Service, is a service in the Amazon ecosystem. It has a bunch of features, but the two I just want to talk about briefly are the concepts of a visibility window and acknowledgements. It works like this. When you pull a message off a queue, you have a set amount of time to acknowledge that you've processed that message. And what happens if you don't acknowledge in that time? It goes right back in the queue. And then if a message is pulled and not acknowledged a configurable number of times, it, again, depending on your configuration, will either go to a dead letter queue or just get discarded. Okay, that should be all the background we need. Reducing speed. Let's take a look at some code. Okay, here is an example of a flow we use in production, although I have changed the function names to protect the innocent. Seems pretty simple, but I will do a quick walkthrough of what's going on here so we can have some context for the rest of the talk. Now in our setup, we have a custom GenStage producer which can pull messages from SQS. When the app boots, we spin up a configurable number of these producers. And then this function just grabs the PIDs of all those producers and feeds them into the flow.fromStages, which means it can start a flow basically, or it's not start because it starts from the bottom. It can pull all, it can get the PIDs of these producers and the events will flow to the right place. The next section, sort of the mapper section, the flow should look most familiar to folk. I could just swap the module flow for enum, and this would look like any old regular Elixir pipeline. This is also the section where most of the application-specific code gets executed. And as you can see by my lovely function naming, for each message that comes in off the queue, we prepare it, which is mostly just taking the JSON, turn it into our main message data structure, which I'm going to talk about in a second. Then we run the message through some business logic, which essentially do some lookups, make some decisions. Then we commit any side effects that are built up in the transformations, and then we also another side effect is that we log any errors that have come up along the way. And then the third and final step of this, we partition by the message window, which you can see in that commented out code above. It's defined farther up in the file. We reduce the partition that comes out by our ACK accumulator function, which is super simple. I'll show you in a second. And then we send whatever's left to that ACK messages function, which sends out to SQS. But why does our window, let me rephrase. Essentially, what all of this is saying is that every 10 messages that comes through the flow, or every 5 seconds, take the message that you have, filter them through or reduce them with the ACK accumulator, and then acknowledge them to SQS. Why only 10 messages? Remember when I said that we should know our system? Well, that's coming into play here. All the batch endpoints in SQS are limited to 10 messages per batch, so that's where we're at. Now, if you're like me, you look at code like this, and a little voice goes off in your head that says, "Hold on, Buster. That looks way too simple to do any real work. There ain't even any conditional branches." And I would say, yes, weird old-timey programmer voice in your head. That is correct. But this brings me to the next lesson that we've learned: use a token. Now the key to keeping our flows simple has been to use a consistent data structure, or a token, throughout the whole pipeline. And the data structure most essential to our flow is the, again, brilliantly named, message struct. The struct is our token through the whole pipeline. The first thing we do when an event comes in off the queue is that we create a message struct based on that. You can think of it like a plug.con or an ecto change set. It just gets passed through the flow, getting transformed along the way. And the consistency of having the same data structure at every step in the flow is how we can keep it so simple. Let me show you the definition of message to elaborate. So this is basically what we have in production, just whittled down to the main fields that are useful. Status does what it says on the tin. It is the current status of the message. The message type is a string identifier that identifies the specific type of message that we are processing. And with a combination of status and message type, gives us a mechanism for lowercase flow control, which I'll touch on next. The body is essentially just the original message that we got off the queue, which is useful for when we're doing message type specific processing. We can pull data out of that. And status metadata is where we can store arbitrary bits about the message status. For example, if the message errored, why did it error? Let's leave that there. OK, so here's an example of how we can handle different kinds of data while keeping our flow nice and simple. Thanks to pattern matching, we can define a different version of the handler for each type of message we need. The only requirement is that it adhere to the contract of a message struct comes in, a message struct goes out, which you can see by the type spec at the top. And there are some clever folk here who are probably thinking that adding a new function definition for each type of data we're processing is going to get messy as the number of types of data gets bigger, and that file is going to get huge. And you would be correct. But if you squint a little bit this code, you can see how we could probably extract out some message type specific code into its own modules and come back and sprinkle a little meta programming on top of it and tie it all back together, which is what we did recently. OK, so inevitably, as Miriam alluded to, something is going to go wrong while trying to process a message. We get bad data coming in, a database is unreachable, something. In those cases, our process is usually to catch the error, or specifically handle the error tuple, switch the status field of the message to error, and put the reason in the status metadata, and then just pass the message on down through the flow. And here's why this works. This is the same code that we had up here a second ago, but I wanted to point out that all the functions, or the top two there, are matching on status of OK. But the final message or the final definition just passes the message through. So anything that's not OK, we just pass along the flow. And we set up all of our top-level mappers this way. Then in the last section in our partition, I mentioned that ACK accumulator function. We reduce across this, and all it really is a filter. So anything that doesn't have a status of error, we pass through. Anything that does have a status of error, we leave. Now remember, the result of this partition reducer is a batch of no greater than 10 messages that we're going to acknowledge, which tells SQS that we processed the message. So again, since we know our system, we know that all of the unacknowledged SQS messages will get put back in the queue, giving us a lovely built-in retry mechanism. Huzzah. However, the thing that keeps this manageable in practice is our next lesson. Isolate your side effects. If you notice the flow from earlier, the last step before batching and acking was to commit side effects. The reason for this is pretty simple. Side effects are mutations. Mutations in Elixir. And if something goes wrong during a mutation, we want to be able to roll it back. So in the spirit of keeping our flow simple, we batch all the side effects together so that it's easier to figure out what the rollback process should be. We don't have to think back through all the modules that this message could have gone through, getting through there. Okay, now I wish this was the part of the talk where I could tell you that one weird trick to make your flow blazing fast that doctors hate me for. But alas, I cannot. How you optimize the flow is very dependent on the shape of your problem. However, what we have learned so far has been how to measure, what can we actually tune, and how can we help outside of the flow. So I'll touch on each of these briefly, starting with measuring. So first things first, we're going to need some graphs. We're going to need some data first, and then we're going to make some graphs. And the procedure we use the most is blatantly taken from an incredibly useful blog post from Timon Tobolowsky, hope I'm saying that right, titled Measuring and Visualizing GenStage/Flow with New Plot. It involves dropping in some function calls at key points in the flow that cast out to a gen server, which records when the action happens and how many messages were there. And after each test run, we can process that data with new plot, get ourselves some sweet, sweet graphs. And this process gives us a lovely sort of tweak, measure, learn framework for tuning the flow. Okay, so now that we know how to record what's happening in the flow, how can we start to tweak it? This is where it helps to know a thing or two about how GenStage works under flow. All right, so here's our main flow again. Under the hood, flow is breaking up the work into 3 gen stages. The SQS producer at the top, sort of a producer-consumer is all of our mappers in there, and the consumer from that partition call on. And it's at those boundaries that we can go in and tweak some stuff and experiment. So the first lever I want to talk about is max demand. This is how much demand or how many events you request from your producers. There's also min demand, but I'm just going to focus on max demand for now. Any of the flow functions that operate at those gen stage boundaries, in our case from stages and partition, accept a max demand option, which just gets passed on to the gen stages that are spun up underneath. Now the default max demand is 500, which is fine to start, but it's generally recommended that you explicitly set your max demand wherever possible in your flow. And by generally recommended, I mean Jose told me to do it, and so I'm like, cool, I'm going to do that. In the case of our mappers, we want to drop the max demand to 10. And this will match the size that we get of the batches we can get from SQS. That way, each demand of 10 corresponds to 1 HTTP request to SQS. We could turn it up, but that would mean us waiting on a producer to make several round-trip HTTP requests to accumulate all the demand before we can start processing it in the message. And that just seems inefficient for them to hold on to it while we're doing more calls. Now, in our consumer, on the other hand, is a different story. So the way we've got this set up is, since we have an unbounded flow of data, we're essentially using this partition reducer combo as a batcher, along with the window that I talked about earlier. So that's how we're getting our batches of 10 or less. So in order for it to work efficiently, we limit the partition to just one stage, but that also means that we can jack the max demand up to 1,000 to reduce the communication overhead between the mapper, the producer-consumer section above, and this one below. No, I just said stages without telling you what it was. Stages are the other primary lever we have to tune our flow. Stages control how parallel your program runs. It's basically how many gen stages get spun up underneath. By default, this option is set to the number of schedulers online in your VM. This is usually the same number of cores you have, or logical cores at least. You could see in my graph earlier, this MacBook has 8 logical cores, so there were 8 schedulers doing their thing. The rule of thumb here is that if your code is more I/O bound than CPU bound, then you want to crank the stages right up. The trade-off being that more stages incur more communication overhead because they're all subscribing to each other and passing data around. Now in our case, our mappers are very I/O bound. They're mostly doing database lookups and confirming things, some file reads, so we can bump our stages right up. Why 100? Well, because that's where the graphs that we made earlier showed that for our specific use case, it stopped being beneficial. We stopped seeing the benefits after that. Okay, the final lever I'll mention here is straight out of the performance discussion section of the flow docs. Avoid single sources. Remember SQS producer function at the start of the flow? If so, you recall that we can configure it to spin up an arbitrary number of SQS producers. That's what we do here. The code's not very cool because it's actually in a config file somewhere else. I just need to put something up there. We may be limited to only requesting batches of 10 from SQS, but that doesn't mean we can't have lots of producers all requesting 10 at a time. Which is a nice segue into working with things that are outside the control of the capital F flow library. So if you're like us, you'll usually find that the bottlenecks in your flow aren't actually from the flow library. We've run into a few occasions where flow is processing the data so fast that it's our dependencies that we need to tune. Two most common examples of this are database connection pools. Basically figure out what our system can handle and leave it way up there. And then also the HTTP connection pools. We have all these producers calling SQS. Sometimes Hackney will limit the number. We just jack that back up. Whew. All right. These are by no means all of the lessons we've learned from using flow and GenStage, but they are all that I have time for today. Here are a few other lessons that I'm happy to discuss if you want to grab me during the rest of the conference. These are other things that I've had to deal with. Folks, thanks for letting me share with you today. Thanks to EMPEX. If you can't tell, I'm pretty excited about Elixir generally, and I'm also excited about its potential in the data processing field. And I would also be remiss to my employer if I didn't mention that change.org is hiring. So if you want to come have an impact on social change around the world, check out that link. Thank you.